Okay, so good afternoon, everyone. Welcome to our NJIT AI Data Sciences Stars Seminar Series. So today our guest speaker is Professor George Karniadakis. He is also my ex-postdoc advisor. And Professor Karniadakis is Charles Peace Robinson and John Palmer Barstow Professor at Applied Mathematics at Brown University, and he's also affiliated with MIT and PNNL. He's a member of the National Academy of Engineering and also Vannevar Bush Faculty Fellow. He received his Ph.D. degree from MIT in 1987, and he was a lecturer in the Department of Mechanical Engineering at MIT, and subsequently he joined Stanford and the NASA Ames Center, and then assistant professor in the Department of Mechanical Engineering at Princeton, and also joined Brown University as associate professor of applied mathematics in the Center for Fluid Mechanics in 1994. And after 1996, he became full professor, and then he's still a visiting professor and a senior lecturer at MIT in the mechanical engineering department. And he received quite a few national research awards, and also AAAS fellow and fellow of the SIAM fellow, and also APS fellow. So today, please welcome me welcoming Professor Karniadakis in joining us for giving this seminar. So the floor is yours.
Thank you very much for coming. Today I want to talk about a new topic, a new direction that I just gave a talk at Delaware last Friday, so I'm giving a similar talk today. Please feel free to ask questions. One of the most noble endeavors in scientific discovery is to discover your own equations. For example, here you're looking at the Lorentz equation. You are maybe familiar with Maxwell equations, the Navier-Stokes equations, the Schrödinger equation, the Einstein equation, and so on. Now, what happens is these equations are very, very important, but it takes centuries and it takes a genius to come up with that equation. It turns out that the Lorentz attractor, you can discover it just with this. It's a simple machine learning exercise. We give you data, and you can actually discover the Lorentz equations. So that's where we are in 2025, and I want to show you some other examples. These are other, like for example, here's the equations. So directly from data, you go to the equations. So that's a huge discovery, right? Because you don't need to be a genius, and you don't need to wait for 100 years. Or some other prototype equations that were discovered using physics-informed neural networks, something that we developed in my group. But today I'm not going to talk about physics-informed neural networks. There's another important paper. This appeared in Science in 2009. And this was a very simple, it's a physics. All of you have taken physics courses in high school. You know that the pendulum or double pendulum, you can observe the amplitude and the angle. And from there, from the data, you can use symbolic regression to get again the Hamiltonian, which is basically the governing equations. So this has been a very influential paper because it was published in 2009, and since then a lot of groups tried to say, can we discover equations? Because everybody would want to give his name on that equation. Okay. So anyway, that's sort of the background that in the last 10 years there have been a lot of discoveries in that domain. And the question I ask here is a little different. Can we also discover algorithms? And again, all these algorithms have their names. For example, here I have two of the oldest algorithms. The Jacobi algorithm is 1840 from the Jacobi brothers. And then the Gauss-Seidel, it's 1874. Long time ago. It's almost so more than a century ago. So let me explain this algorithm because I will come handy later. So let's say you have a PDE to solve a partial differential equation. I write it in this general form with some boundary conditions B. No matter how you do it, you discretize it. And if it's a linear system or a nonlinear system, eventually you have to solve this linear system, AX equals B. We write it in linear algebra. Here's A times U equals F, right? So that's the system that we want to solve. We want to solve for U. And you want to invert A. So what Jacobi said, and Gauss did something similar, break the matrix A into one part which we will call the preconditioner, and the rest of the matrix. For Jacobi, M is simply the diagonal. And it's a relaxation method. It's a fixed point method. If you see here, if you substitute M plus N here, the D, or in Gauss ideal, M is the diagonal plus the lower triangular, and N is the upper triangular. In either case, you end up with a iteration form of this type that says that the next iterate is the inverse of M. So M should not be too complicated. If it's the diagonal, it's very simple. It's one of the diagonal elements. But even if it's triangular, triangular, it's very simple to invert. Times N, the rest, and the previous iterate plus the right-hand side. So this simple algorithm, it's a fixed point iteration. It's called relaxation algorithm. I will explain to you why it's called relaxation algorithm. And it's a 150 years old algorithm. And it works really well. It was forgotten for a while, but now because of in the 80s and 90s, because of parallel computers, it was rediscovered because it's called embarrassingly parallel. It's so parallel, it's 100% parallel, it's embarrassing. So this is the type of algorithms which are good. So, as I said, the Gauss ideal is very similar. So how these methods work, okay, so now let's go forward to the 1970s, 100 years from the Gauss ideal method. This method was developed and was considered a breakthrough. In fact, it increased the speed of how we solve things by a factor of 1,000,000. Huge factor, right? Algorithmic factor, not just the computers. Will give you a speed up, but also algorithms. So it turns out that the algorithm is not a new algorithm. It's actually the same algorithm that I told you, but applied to different grids. It's called multi-grid. So you start here, the fine grid, then you run the Jacobi algorithm, which is called the smoother, a few times. And what the smoother does, it takes the high frequency of the error and smoothes it out, right? So after that, you cannot do much, you will see why. And then you go to a different grid. You project as a coarser grid, do the same thing again, you smooth out with the Jacobi algorithm, and then go down to a very small grid where you can do it on your calculator, and then you interpolate up. So this is called the V cycle. But as you see, there's no new method here. These people, Aki Brown, who developed this in the 70s, took the existing methods and created a meta solver, a very effective meta solver, 1,000,000 times faster than the original one. So basically, you apply repeatedly the same old algorithm. Is that clear? So, okay, so now, why? Let me go into this algorithm a little more. Let's say this is the solution that you're trying to find, U of X. You can decompose it in Wagon modes. So the mode 1, the low mode is like this, the mode 2 is like that, obviously. The high mode is like this one. So what we just said that the smoothers work on this, the error, which will be represented. So they try to remove this and therefore go closer to the exact solution. So they do a very good job here, but not on the low modes. That's how this method. So you have non-uniform convergence. So in fact, if you take this simple PDE, or no D for this here, but it's basically Poisson equation in 1D, and you look at the error versus the number of iterations, you can see mode 1 is very slow. Mode 3 is a little faster, mode 5 fast, and then the high modes are fast. And then this is machine accuracy, right? So you got to machine accuracy with the high modes very quickly. But the troublemakers are the low modes. In fact, if you change the equation a little bit, the Helmholtz equation, you can see mode 1 diverges. So that will pull back the convergence. So it's a non-uniform convergence. Even this very simple example, you can see that you cannot solve it with these methods, although they've been around and we still use them. So the idea, okay, so that's one story, right? The one story is that these methods handle the high frequencies. Now, if I look at the neural networks, let's say a neural network with 2 layers, and I'm trying to approximate this function, the physical domain is the same thing in the Fourier domain. You can see what happens. The low frequencies can fit the low frequencies very quickly, but the high frequencies takes forever. That's why the neural networks could be very, very slow. So here we have the opposite situation. We have the situation where the low frequencies are resolved right away. Maybe I can play the movie again. Oh, actually, it's playing. So you can see already the low frequencies, now it works on the high frequencies, and here you see the corresponding, this very long tail of the spectrum has to do with this discontinuity, that singularity. But anyway, the point is that this is what we call spectral biases in neural networks. So we have 2 complementary approaches. One, the classical one, works on high frequencies, and then the neural networks is good only on low frequencies. It actually does, neural networks do a very, very bad job for high frequencies, really high frequencies. You have to do extra things and do the extra mile and extra work to get, like you can see here, it struggles to get this high frequency. It's not very high. Okay, so what's sort of the big idea? I will explain the big idea. I want to combine the 2, and I want to do it manually, but then I would ask myself, can I automate this process of synthesizing algorithms and come up with the best at all times, given certain criteria? And I will define what is best. Yes, yes, hi.
Yeah, can you roll back to the previous slide? Yeah.
You want to go back?
Yeah. The previous one. Okay. So you're saying that like neural networks struggle. What is the reason behind it? Because of the
Smoothing, over-smoothing, the regularization for many factors. But there's over-smoothing. This is a very well-known phenomenon. So
it depends on how we basically steer the model and train the model. Like lots of components there, right? So
it's always the low frequencies are always easy to get, and basically the plateau that you get in training the neural networks come from fine features. So
thank you.
the regularization has something to do with it. If you don't, then you have noise. But how it the noise, for example, think of noise as the very, very high frequency limit. So noisy versus clean. Yeah. But the only thing for now is I just want you to remember that there are 2 complementary. The classical one, high frequency. The modern ones, only low frequency. I also want to rewrite a neural network. For those of you who have not seen a neural network, here's a neural network. X1, X2 are the inputs. I have one output, but I want to give a non-computer science point of view, or to give a numerical analyst point of view. So a neural network is a function approximation, which is one. And I write a neural network with parameters theta as a linear combination of these weights, which are the weights of the last layer, which is linear layer. In regression, we don't apply deviation functions here, times the basis phi1, phi2, and so on, which is this basis. And in this form, a neural network is nothing else but like a finite element. In finite elements, we have something like that. We approximate a field times the summation of some unknown, or Fourier series. Think of Fourier series is the unknown coefficient times the basis. In Fourier series, the basis is e to the ikx. Here, the basis is actually the last nonlinear layer, and it's an adaptive basis because by changing the data, you can adapt the basis. In the classical approach, you have to change the grids, like we said earlier. Then you change the gradient and so on. So it's a different, it's the same thing, but different thinking, how this is. Okay, so that's how I think of neural networks, as numerical methods. And the last layer is really the basis with respect to which you expand the unknown coefficients, which are the linear weights. Of course, there are weights here, weights and bias here, but these are functions that I will use. Okay, so now I want to tell you about not pins. I'm not going to talk about pins and physics and for neural networks, but I'm going to talk about neural operators and the difference between a function approximation. We map a finite space to a finite space. Like, let's say speech recognition, image classification, ImageNet, NIST, and so CIFAR, and so on. But now in neural operators, we want to, so here we have data in, data out. In a neural operator, we have functions as input, which are infinite dimensional objects. And then the output is also a function. Now, why I want to do that? Because I can solve not one problem, but many, many problems all at once if I have neural operators. Instead of one boundary condition, I will take a plurality, a distribution of boundary conditions. Instead of one material constant, I can take a whole spectrum of material constants. Is that clear? So it's a high level of abstraction, one which you can train offline, and then online you can infer in real time. So it makes big difference. So if you can do that, you can think of an operator as a differential operator or a black box system. In fact, this, if we solve the inverse problem, is a system identification. So that's what we introduced in 2019, the deep operator network. But it consists of two networks, one which has to do with a branch, we call branch, and one is a trunk. Now, we take some inspiration from a human neuron. The human neuron has these branches, or dendrites. These are the inputs. So these are the inputs. So we take all these functions and we put them here. Then we need a space where the computation is done. The computation is done in the trunk or the soma, which is this, which is another neural network. The two neural networks work together. And here you have the synaptic output. Here's the synaptic output. So a little bit of resemblance of a human neuron with what we're trying to construct. And now where's the operator here? Well, the inputs are functions. The outputs are solutions of these PDEs, like S. So it's a continuous output is the solution, and G is the operator. G is the operator that takes functions and let's say the derivative operator. You have a derivative operator. What takes as an input is a function, right? And then what is the output? Another function. So dx is the simplest operator. But you could be this operator, has lots of derivatives. Could be an integral, or it could be a black box, something that we don't know and we try to discover. But it's an operator. Inputs are functions or distributions, a plurality of different scenarios. Okay, so I want to talk about, it turns out that there is a universal approximation theorem for operators, just like for functions, that was discovered about the same time. We prove it for deep neural networks much later. So here is a mathematical expression of what we just discussed. So the trunk is this part here, which is associated with the output. So the output space is characterized by Y. So you can see sigma is my activation function. So this is a shallow network, one hidden layer. And then here is the branch, the input U. So in this particular case, we can take U of X and we map it to G of U of Y, because that's an operator, G of U of Y. U of Y is a function G of U of Y is a function of the output. U of X is a function of the input. We sample it, and then we sum them up at different sensor points, let's say, and then we take the activation function. So this is a single shallow neural network associated with the branch and one with the trunk. But of course, we can make these neural networks as deep as we want. In fact, that's better. Okay, so here I have a summary of many cases where we solve, let's say, this equation here, like a divergence of some unknown field, or known or unknown field, times the H, gradient of H. It's called for porous media. This is elasticity equations. This is equations from chemical engineering, and so on. So you basically train them the way I discuss, and you can train them on these domains. And it turns out that with a little bit of transfer learning, you can also transfer them to different domains, different states. For example, here we train on a limit cycle, and we can transfer to a fixed point. So in this case, the operator is all these differential symbols here in the second example, right here. The operator is all this. So we'll basically learn this operator on the fly. Now, as I said, DeepNet gives you a plurality of neural operators, and you don't have to use, you can use graph neural networks in the branch, the green part, or spiking neural networks. I work on with spiking neural networks these days because they're energetically more favorable. And the same thing in the trunk, you can use convolutional neural networks. You can do whatever you like. So this is the space associated with the output, how we express this operator, and this is the space that incorporates the inputs into this, and then the two work in sync together. So that's one type of operators. There's some other work on neural operators under the name Fourier neural operators from Caltech, and they work a little different. If you use Green's theorem and Green's functions, you can write a solution as a summation of the Green's functions times an input integrated over the dummy variable tau. Here they added this correction, but in this operator, they don't use the Green's functions because the Green's function is a linear concept. They use this learnable kernel, so you have to learn that, and then you have to learn also this weight matrix W. V, as I said, is the input. And there are all sorts of different neural operators under different names. How do you do it exactly? Since this calculation involves a convolution, you can use transforms like Fourier transform, you can use Laplace transform, wavelet transforms, and you can compute this fast. Again, at issue here, so this is how the FNO, for example, looks. You take an input, you put it in the high dimension, then you put many of these Fourier layers, many means 4, 5, and so on. So notice what happens. I take the W matrix here, I add it here. This is a Fourier transform where I do the kernel, and then you apply a nonlinear activation function, and you repeat many times. Then you project it down, and then you have the physical outputs. So it's a typical method of doing this type of operator. So what I just told you, there's actually right now a zoo of different operators. So it's not just my operator, which was DeepNet. There are other people who are competing with me. They're not as good, sorry. Just kidding. They're all different operators for different usages that you can use. But you don't know, as a student or as a researcher, say, when do I use FNO, when I use Laplace neural operator, when do I use DeepNet, and where do I use the variants of DeepNet, and so on. So that's one of the questions that we'll ask. Now, this was a sort of background material to get to the point where I want to develop a new algorithm. So the classical Jacobi algorithm that I told you before is this one here. I want to solve the system, A equals F. I initialize, I find a correction, I update with a correction, I check my residual. If it's small, I'm done. If not, keep repeating this. And it takes many, many iterations because, as I said, initially the algorithm converges very fast because it smooths the high frequencies, and then it stalls at low frequencies, cannot do anything. So I have a very, very simple idea which comes from what I told you earlier. So I want to replace, let's go back. I want to replace the standard solver, the 150 years old solver, with something, not totally replace it, use it sometimes, but also use a neural network here, a neural operator that learns it. Why I do that? Because I want to tackle the high frequency and also the low frequency. And neural operators, remember, they learn the solutions, roughly the solutions. I don't need to do an excellent job. I just need to get the coarse resolution done. So in other words, I don't need to train my neural operator to be excellent, just to capture the low modes. It's good enough. So then once in a while I will call this, once in a while I will call this, and do the same loop. So I'm not changing Jacobi, I'm just enhancing it. Is that clear? Any questions? So it's a very, very simple method because this doesn't cost anything. I told you, you pre-compute everything, and this is also embarrassingly parallel. So now you have a really, really good algorithm, and you can write a paper about it. So now we wrote this paper. So if you have multi-grid, you can actually use also multi-grid and do the same thing for different grids. Exactly what I told you for different grids. But you don't have. Okay, so let's see an example. of the equation I showed you earlier. If I use Jacobi, every iteration, you see the error? So it's not very good because of mode 1. It doesn't really go down. It goes down, initially it goes down, and then if I go only deponent in the beginning and then Jacobi, nothing happens. If I go Jacobi, deponent, JD, look what happens. Okay? Very, very simple idea. I combine the spectral bias of neural networks with the Jacobi property to have something new, a meta solver. Okay, so that's sort of the idea, but of course these are old methods. These are the newer methods. In the 50s and 60s, people developed conjugate gradient methods, Krylov methods, various versions of Krylov methods. So there's also a zoo of methods, of standard solvers. So I want to create meta solvers using neural operators, and there's a zoo of neural operators. Then there's a zoo of methods. So now you have two ways. You hire 12 PhD students to do this for you, or you come up with an algorithm, how to do that automatically. So it's cheaper to do it automatically. So let's do that. Here, I show you how you can use the course. From the deponent, you can get the trunk, you can get the, which gives you the basis to do the course preconditioner for these Krylov methods. I only talked about the relaxation method, but they work the same way. So we have new approach, new questions. Are these hybrid solvers, are they always better? How much improvement you can obtain, and then what is the optimal solver, and we define what optimal means. The answer is yes. So I give you here lots of results, but I explain it. So here we solve a 3D scattering problem, scattering, let's say, acoustics from a submarine, trying to detect a submarine. So you solve this wave equation in 3D and time, and you have to solve the system. You can see the Jacobi methods, all these relaxation solvers are not good because they diverge for this problem. It's a hyperbolic problem. Now, if you include it, if you combine it with deponent, they converge. If you combine it with, if you use Krylov methods, are very good. Combined with deponent, they give you the fastest solvers on Earth. That's what we call it. Cannot beat it because it covers all spectra. So the speed up here, you can see we go from, if you use this method, which is very sophisticated conjugate graded methods for non-symmetric matrices, non-positive definite, from 791 iterations, you go down to 14 with no extra cost. That's pretty good. I would buy that. And then from here, over 1,000 iterations, you go down to 19 if you use GMRS. So instead of using GMRS, you use GMRS plus some combination of neural operator, this hybrid. Okay, so just to show you that this, so we work with ANSYS, which is the largest software company in the world. So they do real problems. So here we combine the same thing, combine the two, but actually we train deponent not on the target geometry, on a geometry like this, up here. And then we try to do it on this another geometry without even transfer learning. And because we are only interested to capture the coarse mode, the low mode, we don't have to do a perfect job. It's enough. And you can see how much we beat ANSYS. And this is ANSYS, they're the secret sauce, the algorithm. Okay, so I think I motivate the fact that it's good to produce meta solvers, to get ideas. Don't discard the old ideas, right? Jacobi was a very smart guy and so on, but they had their limitations. So now with neural networks, we don't have to throw out everything. That's sort of the message here. But we want to do better. We want to discover this automatically. So I came up with this Omega framework that is currently a project. Omega would mean the final word. So A to Z, we say Omega is in Greek alphabet, is the last alphabet, the last letter. So Omega is the final answer. So we have a grant from DARPA under this electroneering program to develop this. And so there are many ideas here.
Quick question.
Yes, of course.
What is Phoenix AI?
Physics AI, it's not an easy. Yeah.
So the last author.
Oh, what is Phoenix AI? Oh, it's a company that I co-founded with one of my postdocs. And they
I thought it's an LLM, that's why I'm asking.
it is an LLM. It is an LLM for these things.
Okay.
So it's a copilot to write scientific computing programs like pins and neural operators and so on. Yes, yes. Yeah, yeah.
Would you list Phoenix AI as a co-author on the paper, though?
No, we list other.
Okay.
So, good question. we may consider that in the future. Okay, so here's a workflow. We go from left to right, but what I told you so far, there's many different solvers, one silo, and then there are many different operators, another silo, and we want to take one of each and mix them. But there are many, as you can see, there are many combinations, and then depending on the data, on the problem, and so on, you have to change it. So we want to automate this process where the LLM, Jim asked, where that comes in here to write this code automatically, and even some very minimalistic instructions from us. We write the code, and also we have this RAG because you can do some enhancements in the whole process and so on. So it can be a learning model. But we haven't completed the whole thing yet. But the point here is that I want to formulate an optimization problem so that I don't have to have 12 PhD students. I actually have 12 PhD students, but everybody is working on different topics. I don't know why I choose. Okay, so here's the idea. The idea is, first of all, you have to formulate some metrics. For example, how much does it cost? What is the error? The number of iterations, the memory, the robustness, and other issues, right? So these are your metrics. And then you have to find a minimum with respect to these metrics. So you will sample that multidimensional space, and you come up with all these points. Let's say if we have only two metrics, the error versus computational time, which makes sense, then you have from all these points, you can find some surface. Here in this case is a line, this yellow line, which is called the Pareto front. How many people heard of a Pareto front before? Yeah, some people. Okay, so it's basically the best solution. But as you can see here, all these are good points because this here has low computational time but high error. This one here is the opposite. So all these points are acceptable. So doing this multi-objective optimization will give you lots of different solutions. Of course, we can disregard all this, but we don't have just one solution. We have a Pareto front, so we can establish the Pareto front with offline work. So the Pareto front is a very important topic. Just to give you an example, let's go to this one that we talked about more extensively. So for example, I assign a variable x1, which will parameterize which one of these neural operators I will be selecting. Then x2 will select the solver, Kolbe-Gauss, ideal, symmetric, over relaxation, whatever. And then here, the x3, how often you use this compared to this? Because I go back and forth. You don't have to go to alternate. You don't need to use that. There's an optimum, a sweet spot, there's an optimum point. And then also, you can say how many levels of multi-grid if you use multi-grid. So there will be several variables there. Same thing for this other type of solvers. So again, the metrics are here. Computational time, so I have a 7-dimensional space. I'm looking for an optimum multi-objective because I have 7 objectives. I will want to minimize with respect to computational time, want to enhance convergence rate, number of iterations, and so on. Here's the number of multiplications and additions, and so on. So I want to minimize with respect to this multidimensional vector, and I want to also talk about preference function. But I will show you all this in the next slide, how I set up the problem. So, as I said, the Pareto front is not a unique solution, but you need to introduce, or we introduced, a preference function. In other words, what is very important for you? For example, if you are a mathematician, you care about the error, you emphasize the error, and you don't care about the speed because somebody else will do the work. If you're an engineer, you care about the speed, you don't care about the error, because you're going to use a safety factor anyway. If you're a physicist, you're somewhere in between. So you want to put emphasis on both. So in other words, we introduce a preference function where we combine these weights with these lambda i's. So if lambda, let's say F1 is the cost, F1 is the error. If lambda 1 is 1, and all the other ones, lambda i's are 0, then we only care about the cost. But in general, we'll be interested in a linear combination of all this or a nonlinear combination. Because you may want to say, if I achieve certain accuracy, after that, I really want to finish quickly. I don't care about the accuracy. I'm an engineer, 10% is good for me. But you have a preference function, okay? And we'll see different preference functions. But if you now have preference function, you formulate the optimization problem where we have the Pareto front, which is some surface, the line in 2D, and then you want basically to intersect. The preference function is also functions, so that function will intersect the Pareto front. Where the intersection is, that will be the unique solution, which will be your best algorithm with respect to those criteria. Is that clear? So, go ahead.
Questions. You have 4x over there, like the operator, neuron operator, some, and the 3 is the ratio between the two. You set, like some value there, and basically you try and get this, like Pareto front. Is there a way that you can just learn the actor as well, for example, like uses like a model that makes just a mixed combination between the two and learn how they combine together using a tensor weights, or like a mixture between the two?
If you have two only, I think you can do it. Yeah. But if you have 7 or 12 and so on, that's very, very expensive because there's an exponential work.
Have you done that with a small number of operators?
I've done 3, but I haven't done it with it because this problem here reduced to a linear programming, which you can solve in a second on a MATLAB.
I see.
So we reduce the high-dimensional problem with a preference function to a linear programming.
Okay.
So you cannot beat linear programming.
So that's the key.
That's the key. That's the key. But I have a sketch here. So here's what we're talking about. So remember, we have all these choices because you parameterize all the solvers and all the parameters for the neural architectures and so on. And you find the Pareto front. So that's a lot of work to do, but let's say we do that. Now I said, if you have a certain, let's say, preference function P1, you intersect the Pareto front, the orange line, with that surface, so that gives you a unique point, and that's really the solution. So this is the optimal solver discovered by P1. Now, somebody else has a different taste, so you change your preference function to P2, emphasizing more the speed, so you can find, for example, of the error, you can find this intersection now, and so on. So you have a different solver. So this is actually a real experiment. You can see all these blue points. You can see here the outline here, the Pareto front, and you can see using different preference functions, we can find different solutions. Here I have a real example. I told you about the submarine, scattering from a submarine like that. So that involves, again, solving this big system. So here's some math behind it. It turns out it's a complex boundary conditions. Now, here's something interesting that you will say, well, did you spend a lot of resources to train DeepONet for this scatterer, and how do you know the scatterer since you're searching for it? It turns out that this neural operator, you can train it without any scatterer, because it defeats the purpose. Just solving this equation in a homogeneous box without any scatterer, and that's enough to give you the correction that you want. So that really saves the day. But you train, as I said, on the box, and then you transfer it here. So this is what I said here. You train the neural operator on a clean box, and then you can transfer it to a box which has to a domain that has a box, cube inside, or another scatter, or a mine, or something, whatever you're really looking for. Okay, so here's some solutions. This is in 7-dimensional space, so I have to project in 3-dimensional space to see. But you can see that this surface is not even continues. And there are 3 different visualizations depending on the measures that you're using. So you can always find the Pareto front. Here's an example. Somebody who is conservative wants to equally weigh all the 7 metrics, right? So it's the average of all the performance metrics. And this table here tells us that the top solver was to use a neural operator DeepNet, to use this FPICG stack, to use 2 levels of multigrid, successive over relaxation, and then do 3 smoothings, use DeepNet, 3 smoothings again. Now, it will take a graduate student about 5 years, about his PhD, to come up with this, to beat that. Here we can do it after you establish the Pareto front, you do it in 1 second, which is the MATLAB part. And the same thing, the second best, using the same reference function, you find something different, and so on. And you can see here all the metrics. So the point is, we automate the whole process to just, for the user. Here's another one. So here now I emphasize computational time and error more, and then I give a little weight to the other measures. So I take all measures into account, but not as strongly. And then you come up with a different algorithm. For example, here you have 3 level, here you have successive over relaxation, and so on. So you pick up, because remember, this is a meta solver. It's a combination of lots of different things. It's synthesis of lots of basic tools. And again, you can look at the time and number of iterations, for example, 6 iterations, which for this problem that we're looking at, a 3D submarine, is very fast. And of course, you have, for that problem, the reason we chose this problem for DARPA is because we have to detect the submarine fast, otherwise they will shoot us. So better we discover. Okay. This is just another application to show you the same thing happens. This is from ANSYS, it's power electronics, different equations. If you use this reference function, you weigh the metrics. You find here Gauss-Seidel, for example, is best. So different methods give you different combinations, but all these are different discoveries. And again, this is what I told you earlier. There's a huge, here's like 8,000 iterations, 3,000. But it goes down to 17 iterations. So there's tremendous advantage of using, so you can develop your own algorithm, you can give it to your own name and so on. Now, the last piece I want to tell you about is, how about neural architectures? Because you have to design architecture and you have to say, okay, I'm gonna use this architecture or this architecture, and the specific question that I am asking is something that I'm sure you all have dealt with. How to forecast time series. Could be the weather, or it could be seasonal products for Christmas, for example, women's shoes or something like that. Whatever, commercial machine learning or scientific machine learning. You are forecasting something using the past, okay? The applications that I will look at is forecasting my glucose level in the future by taking measurements in the past. Okay, so this has been a very active area of research in the last 10 years, started with about 2017, for example. This is a paper from 2019, the review paper that shows that you have some search space. You choose one of these strategies, you evaluate it, and then you iterate. It's a very, very time-consuming method. If you ever use AutoML of Microsoft, for example, you know what I'm talking about, or they use Bayesian optimization and so on. Yes, here's an example where you look at the probability and then of that architecture. Then you look at the gradients. So it involves a lot of expensive operations. You can use reinforcement learning here, for example. But that's not what I want to do. I want to forecast time series, and I'm asking the question, maybe 5 years ago, for time series, the default architecture was LSTM, right? Long short-term memory, which was used almost exclusively for time series dynamical systems or otherwise for commercial systems. GRU is a simplified version of that, has 2 gates less than the LSTM, and it's also faster. And turns out it's really, really robust architecture. But then transformers came along for ChatGPT, and then people found that forecasting time series, especially for phenomena that are non-local, transformers are very good. But they're expensive. You take long sequence, long time integration. So then state space models or Mamba came along and says, well, Mamba is better. So now what is better, Mamba or transformer for time series? What do you think? Well, there was another paper, follow this paper, not Mamba, but Jamba.
Okay.
So what Jamba was, let's use one of this and one of this. Because, okay, I can predict time series better. But they forget to say that if you use the same architecture on a different time series, they get completely different answers. So there's no one universal answer, and I already told you, there's no one universal answer to what is best or what is optimal. Optimal is with respect to your own preference function, okay? If you're a boss, you're conservative. If you are a young student, you're very bold and you choose different weights and so on. So I want to use, the idea therefore is, I want to use, just like I did before, I take all this together and then discover which one is best. So how do I parameterize this? Well, I'm going to use a composite architecture. I'm going to use Jamba, the SSM, K blocks of it. I'm going to use J transformers. I'm going to use M LSTM, and I'm going to use N GRUs. Now, if K is 0, means that this is not, if I find K to be 0, because I will parameterize, then that's not there. How about the sequence? I will also make the sequence one of my variables. Okay? I'm not going to commit to any, I make that a variable. So here, I have 3 dimensions, the relative L2 error, training time, a number of parameters. Before I had 7 here, I make. Now, what's my parameters? Number of each block, NMJK, so how many blocks you get from each. The sequence of blocks, X2, which one goes first, second, third, and fourth, and so on. And then the hidden dimension, this one you can increase, but hidden dimension will be, for example, how many neurons, how many layers for each of the block. But you can see now, depending on the architecture, you can put many more parameters here, right? You can parameterize each block with another 10 parameters, the learning rate, and so on and so forth. So I have many applications here. I'm going to show only this, and then I will stop. So this first application is, as I said, is about predicting glucose trajectories for the next 2 hours. So, you know, that's very important, for example, to prevent any hypoglycemia or hyperglycemia events. But basically, you're monitoring your glucose, and you may have many patients here. I forgot how many we have, 90. And you are looking at the past, and you're trying to predict the next 96 time steps, which amounts to 2 hours. 2 hours is plenty. Basically, you can decide, do you want to eat that tiramisu or not? Okay, so that's very important. So that's sort of the problem. We have data is real data. So how we parameterize this? Well, I said that we introduce a variable x1, which I cap it from 0 to 2 here, so I can have up to 2 blocks of each. The hidden dimension will be from 16 to 64. And then x2, you can expand this list, but x2, I have various combinations here, which I thought they would be interesting. So then you can choose this sequence. In terms of preference function, the first one will be the average, the conservative. Second one, well, I only care about accuracy. Third one, I care only about cost. And another one will be sort of a mixed one. Not exactly the average, but 60% accuracy, and then the rest is cost and so on. Okay, so doing that, again, we find a Pareto front, as before. Find lots of points. This takes a lot of time to evaluate. But finally, you find a Pareto front, which is visualized here in 3-dimensional space, somewhere here. But there are lots of solutions there. And then you say, according to a P1, the preference one, which was the average, the architecture is, I put first GRU and then LSTM. No transformers, no Mambas. If you care about the second one, let's see what P2 it was. Sorry. P2 was this preference, the accuracy. First one was the average. If you care about accuracy, you get a more complicated architecture, 2 GRUs, 1 Mamba, 1 transformer, 1 LSTM, and you can see the error. The error is much smaller than everyone else, right? And here, and then if you care about the cost, it's this one, and the GRU only, but the error is about 7% now, but the cost is only 6 compared to the other ones, and so on. So you can see that indeed the preference function does the right thing. So that's a key, very simple idea, but the key idea, and also very useful because it depends on your point of view. If you are working in an insurance company, if you're a scientist, an NASA scientist, or if you're a civil engineer, you have different criteria on how to do this, what is optimal. And here are some of the architectures we discovered, as I said. You can see these are composite architectures. And also remember, we also modify the interior of these modules, not just the sequence and the number. And this was for the accuracy, and this was I forgot what that was this here. Now, here's another question. Can you, if you give me an architecture, you can give me an architecture, you put together, let's say the Jamba, right? One Mamba and 1 transformer. Then you can ask me, what is this good for? This architecture will be best for what? It's a good question, right? It's a sort of the inverse. Because before we define the preference function, and we said what's the best architecture. Now you give me the architecture, and I have to tell you, is that good for anything? Okay, you may. So the answer is, can you find these weights in your preference function? You may find 0, 0, 0, for which case your method is crap. But in this case, for example, I put a transformer and an LSTM together in this sequence. It turns out that you can see here lambda 3. Can go back to what is F3. F3 is training cost. So this architecture here, you can anticipate it will be very fast. It will do a decent job also in the error, or on the average, it will do a decent job. This is the error. This is the error here. If you use GRU, I think that's the cost. You emphasize the cost, and we already talked about that. And then if you care about the accuracy, you put 1 here, 0, 0, only about the accuracy. So this architecture is good for that. So you can solve the forward problem, find the best architecture for my preference function, and then I give you an architecture, what is this good for, this architecture. So you can solve these problems both ways. Okay, so basically done. I want to summarize and say that you can use parameterization to discover different solvers or neural architectures. And of course, the same type of approach could be used in different fields, where you're looking for something optimum or semi-optimum, because with the preference function, you can control that. It's like a switch that you can say, okay, I want to put the emphasis here, but not too much emphasis. So here we solved a multi-objective optimization problem, and we established a Pareto front, but we obtained unique solutions by introducing the concept of preference function. All my preference functions I show you are linear, but actually the most interesting part is to be non-linear, because as I said, sometimes you say, well, I want to get a certain accuracy, but this is my budget. This is how much computer time I have. And also, I don't have much memory. What can I do with the memory that I have? So that you put a cap on that. So all that can be packed and encoded into the preference function. So it's a new concept. We introduced that. I think it's a very useful concept. Now, the cost of establishing the Pareto front is expensive. People who work on design, they know that. You have to do a lot of work. And here, the higher the dimensional space, we had 7-dimensional space, the higher the cost. So the idea is to develop smart sampling techniques, depending on the sensitivity of these parameters, to sort of adaptively go and sample the multidimensional space. So that will ease the cost of offline training. And then I didn't tell you something, the most important one, but I did show that the Pareto front is like that, right? But remember, I show you solutions here and there, but there are also a bunch of solvers, or good architectures that are in the non-convex part of my Pareto front. But linear programming will not give you that, right? It will be great if I do linear programming to find minima in non-convex functions. Would that be great? It will be great, but it's not happening. So you convexify this, so you can find sort of solutions that don't exist. But if you really want to go in here, you have to do something else. And these days we're trying to go to something called differential games. But basically there you have to solve a minimax problem. And that's more difficult to solve. It will not be done with MATLAB. You have to develop code. So that's what we are currently at. I just want to also say something about my centers that support my work. So we have this physics-informed machine learning. Machine Intelligence Center is called CCROGS. The acronym is down here. Actually, Menja is part of this center. There's a DOE center. It involves Sandia, Pacific Northwest National Lab, Brown, Stanford, Caltech, and JIT. And you see there what we emphasize is neural operators, graph networks, and spiking neural networks. As I said, this is one of my current areas of work. And also I have a MURI that I direct, which unfortunately is ending this year. And this was used to develop physics-informed neural networks and algorithms, applications, and so on. So I will stop here. I'll be happy to take questions, and thank you very
much. Questions?
Thank you for the seminar. I have a lot of questions, but I think I'm gonna do 3.
Use a preference function.
When you showed the architecture of deep with Jacobi, gate, no, is a stochastic or you put a special weight of?
No, this was actually one of the parameterizations. So we left it as an open as a parameter, and then you find how often you have to go to DeepONet. I think we found like every 5 times you go to DeepONet. You don't need to go, because the example I show you, I was going Jacobi DeepONet, but actually you have to go every 5 times. But it will depend on the problem. So when I did the optimal, because imagine you don't know how much frequency, how low frequency and high frequency you have. So when I did the parameterization, that was one of my parameters that you have to determine on the fly. Yeah.
Other it's about the degeneracy of the solution. What kind of to know if a good solution or not using the Pareto front, the reference function? With that, you have a family of solutions, or you have just one solution?
Yeah, because it's a linear programming, and you have you guarantee that you'll cut the convex part. That's what I was saying at the end, that there may be a bunch of solvers or good solutions inside that non-convex pocket. You will not be able to find them with linear programming. So you have to do something else. You have to do these differential games, which is sort of like Nash games, Nash equilibrium game types, minimax, subtle points. So it's much more difficult to obtain. But we don't have results on that. That's why I didn't show you.
And well, and the last one is about graph structured data. I saw that you are now working on it. There is any work that you have working on graph structured data directly with graph method and
the graph neural networks? Actually, this is a big consortium, so I'm not the ones who work. Actually, Menja Shu here and some other people from Caltech are working on this part. So it's not, that column is not mine. I leave it for somebody else.
And also some PI from UPenn.
Yeah, the UPenn. Yes, hi.
One quick question.
Sure.
You see the Pareto fronts, you have to sample a lot, right? It's very costly there. Right now, do you have any theoretical bound for the Pareto front approximations that, say not this is good to a certain level, or? Yeah.
Oops. Yeah. So no, the only so you have a bunch of parameters, right? That makes your multi-dimensional space. The only thing you can do is, I mean, one thing I can do, we don't know the answer to your question, but one thing we're thinking to do is to look at sensitivity of the response with respect to these parameters, and then extract weights, and then sample the most sensitive regions for these parameters heavier. So that's kind of what we're thinking. But right now, if you do a sort of a grid search in even 7-dimensional space, it's very expensive. Yeah. So that's really the real cost. After that, at least for the linear programming we're doing, there's no cost. When we go to the case where we're trying to find solvers, hidden solvers in this part, that will be difficult because you want to be able to cut part of the non-convex part. And of course, there may be multiple non-convex pockets, so that's expensive. But right now, that's still empirical. Yeah.
So,
there are no guarantees of any sort, theoretical guarantees.
I saw your reference function is linear right now. So I'm wondering whether you're going to learn the distributions of those directly. It's not like, instead of like doing a linear.
Yeah, I don't know if you could in principle, if you are willing to spend more time and more money, but typically in the applications, you know that, let's say you're looking at specs, right? So you know that you want 3% accuracy. So when you reach 3% accuracy, you put an if statement. If epsilon less than 3%, then that parameter is not, don't sample with respect to that anymore. But then you emphasize cost. You want to finish quickly. So these are non-linear. In fact, the other applications I show you, our engineering applications, have more realistic preference functions that people who work in the field gave us, and they're non-linear.
Yeah,
now, to learn the preference functions, I think from historical data, you can do that.
It's very expensive.
It could be expensive, but you learn only once in a specific field. So,
okay.
So I don't know. In manufacturing, let's say you manufacture the same thing every day, and every day, eventually you have so much data, you can learn your preference function.
Okay, I saw there is a question. Arena, what's your question? Can you hear us? Yes.
Yes, in terms of iterations, we were 100 times, at least 100 times faster in terms of iterations. In terms of cost, it was about 10 times because, not because deep net was expensive, but because I think of data transfer. So we didn't actually try to optimize that part. So, but I would say a factor of the order of two orders of magnitude at least you gain with existing solvers. So the way we have constructed the method, it's guaranteed to always beat the existing methods. Because let's say you start with conjugate gradient plus the neural operator will give you at least 10 times faster method in terms of cost, 100 times in terms of iterations. I think with some work also on the implementation, like in JAX implementation, that will be 100 times or 1,000 times faster than existing methods. So we guarantee that we have the best solver on Earth. Now, the speed up is currently on times 10 for the problems I show you. On iterations is 100 or more. I forgot the other question. Yeah, right. Yeah. So the data is actually done by the physics. For example, all the deep nets here were trained not by real data, by just solving at the course level, solving these PDEs. Now, if you have no PDEs and this comes from a black box, yes, you will need data to train the neural operator. But again, we don't need to train the neural operator to capture the high frequencies, which is the expensive part of neural networks. We only need to capture the low modes. So very, very coarse. So coarser data sets would be appropriate for this case. And that's, I think, what saves this approach. No, because well, for the solver here, that comes from the relaxation method. So the DeepONet itself, the neural operator itself, does not need to know the high frequencies, because, as I said, because of the spectral bias, that's very expensive training. So think of DeepONet as a preconditioner. If you come from linear algebra, you know what I mean. And the preconditioner, the coarse grain preconditioner is the expensive one, it turns out. That's why multi-grid, you project down, you don't project up. You project to a coarser grid. I can explain offline also.
Yeah, I think we will have a meeting with you later, right?
Yeah, we can explain it at our meeting.
Yeah, that's the last question.
I have a question. So you introduced the concept of preference function when you apply the neural operator into it, right? But after that, you use the LSTM application. So I have a question. So is there any restriction for the preference function, like just only applying to the neural operator? It could apply to any kind of learning algorithm out there.
In the second part, when I talk about neural architecture, there was no neural operator.
Yeah, that's right.
So it was a totally different problem, right? I think what I show you is that this framework of optimization can be applied anywhere as long as you can parameterize the competing trends of the system that you're studying. You parameterize that, then you try to find an optimum. Nothing to do with neural operator. I use a neural operator in the first part just because I wanted to improve the existing solvers and create a meta solver.
I see. So because of that, like, I'm not clear of the true
preference
of the open net, of the neural open net, because because the problem of preference cost and open net is two different problems that you're trying to solve.
The preference function has nothing to do with the optimization problem. It's only at the end to give you a unique solution. The optimization problem gives you a Pareto front with a bunch of solutions. They're all good. The preference function tells you from that Pareto front, because I like speed over accuracy, I can find a unique solution. So that's it. So you as a user come in and say, well, you go shopping, right? There's the lower shelf and then the upper shelf. So the upper shelf are the good stuff. So you can choose which one, because that's your preference. So that's how it works.
Thank you.
And then you, although there's a bunch of good stuff here, you choose the one that you like. That's your preference function. So that's how it's unique. Of course, if you're greedy, you can choose all of them.
Thank you.
Okay.
Yeah, thank you, everyone. I think the seminar will be here, and we will have another meeting with our associated team next month in the other office.
Okay.
Thank you so